Hey guys, welcome to another video. The purpose of this guy is to start trying to look at how chemists represent different events, I suppose, in the real world as chemical equations. What I mean by events is anything really. So if you love fishing and you take your tinny out and you go fishing, you catch a heap of fish, and you bring it back and you don't hose your metal boat off, and you leave it for 2 weeks, 3 weeks, 4 weeks, and it's got salt water sitting on it and it starts to rust and corrode and break down, then that's an event. That's a chemical reaction that's going on, and we can, as a chemist, we can represent that with chemical equations where we sort of talk about what's going on. Inside your body, you've got cellular respiration going on. We're taking food and you're turning into energy. That's an event. That's a chemical reaction that's going on that we can represent as a chemical equation. Plants going through photosynthesis, there's a chemical reaction that happens so that they can store that sun's energy as food, and we can represent that as a chemical equation. And so the purpose of this video is to start to learn how to, or remind ourselves, refresh ourselves on how we do that, how we write those chemical equations, and then how we balance them. Okay, so the event that we're going to look at, or the chemical reaction we're going to look at, is one that we've seen before, sodium metal in water. So I've written it here as a word equation. We're going to break it down and turn it into a chemical equation. So here on the left side of any chemical equation, we've got what we call our reactants. Our reactants are what we start with. They're the chemicals that we start with. So in this case, we're starting with two different things. We're starting with sodium metal, which we can represent as Na. And I'm going to put a little S down here for solid. So that tells you the state at which the element's in. It's in its solid state. We saw that. Sodium's a solid. You can chuck them in the water. Water, we can write that as a chemical equation as well. That's H2O. And he exists as a liquid most of the time. So I'm going to put a little L down there just for liquid. So these are our reactants, and we know that if we put these two guys into contact with each other, a chemical reaction occurs. And a chemical reaction is really just where bonds are broken, and then bonds are formed, right? Electrons might be transferred, or that sort of thing. So we've got our reactants, and in this case, it's sodium metal and water, which when we put them together, will react and will actually form what we call products. All right. So what do we end up with at the end after everything's happened? What do we end up with? They're called our products. They've taken on a new identity. The same atoms are there, right? So don't get me wrong here. The same atoms or elements will be there. Sorry, not atoms. They might be ions, but the same elements will be in the products, but they might have been rearranged. Okay, they might have been, bonds have been broken, bonds have been formed. Think about it like, some Lego, right? So if you build an awesome castle out of Lego, and then you decide, I want to change that into a pirate ship. You got to take that Lego sort of castle, you got to break it down, you got to turn it into a ship, right? You've still got the same blocks, but you've made something totally different out of it. That's sort of what a chemical reaction is. That's what we're trying to represent here with the chemical equation. We started with, sodium, metal, and water, and we're going to finish with something different, which we call the products, but it's made of the same stuff. So in this case, we've got two products. We've got hydrogen gas, which is H2, and we've got sodium hydroxide, which is sodium and a hydroxide, OH. And he's going to be dissolved in water. If it's dissolved in water, we put aqueous. Aqueous means dissolved in water. So these two compounds here are our products, right? So just as a revision really quickly, we know that hydrogen gas is a molecular compound. He's covalently bonded. So we can actually draw him. And I might put him above here. He's covalently bonded to himself, sharing a pair of electrons in there if we really want to put them in. That's hydrogen gas. We've got sodium hydroxide here. So we've got a metal, and this hydroxide is a polyatomic ion. Previous videos talked about that. So he's a non-metal, and we've got a metal. So we've actually got an ionic compound that forms here. This guy's like a crystal. So we've got sodium ion, which is Na+, and we've got a hydroxide ion, which is OH-. And when they come together, we've got one positive charge and one negative charge, and so they come together and cancel each other out, which is good, and forms what we've written here as sodium hydroxide. I'm just going to rub him off. So we've actually got an ionic compound there. If you really want to put in the bond, there's a bond, but that guy's an ionic bond, not a covalent. Over here, just so we're consistent, we've got water. So we've got an oxygen here, bonded to one hydrogen, and 2 hydrogens. We actually got him bonded to 2 hydrogens. So this is what his structure looks like, H2O. Those are covalent bonds again because we've got 2 nonmetals sharing electrons. If you really want to be awesome, you can put in the other electrons that oxygen isn't sharing that are there. And we've got sodium metal. Now we didn't talk much about metallic bonding at all, but he's just a sodium atom. Okay, so that's what we've got currently. So we've got our reactants and we've got our products. So this is a chemical equation. This shows us what happens. This is representing that, when we throw sodium in water and it explodes, this is sort of the reaction that's going on. The explosion sort of happens because of hydrogen gas being flammable, but this is the process that is occurring as a chemical equation. Now, the last thing we've got to do is, when we're writing chemical equations, is that we need to balance them. Now, I've already talked briefly about why we have to do this, but we have to balance equations because at the end of the day, as chemists and in the real world, we can't, when we go from reactants to products, we do not lose atoms or ions, we don't gain them, we don't magically make them up or make them disappear, they just get rearranged, right? So whatever's on the left side of the reaction has to be accounted for on the right side. It's called the law of conservation of mass. So we have to maintain our mass from the left side to the right side, just like if we had a pile of Lego and we built a castle out of it, and then we broke it down and turned it into a ship, a pirate ship or whatever we want to do. Your Lego blocks, you've got to have the same number. You haven't destroyed any, you haven't lost any. There's the same number on each side. You've just rearranged them. Okay, so balancing equations is all about making sure we account for all of the atoms that are on the left side and the right side, making sure they're all there. Now, the way that we balance equations is by putting, where needed, coefficients in front of each of the molecules or the compounds that are in the equation. What I mean by coefficients isn't like a whole number most of the time normally, so 1 or 2 or 3 or 4 or 5. So that's all we can do. We cannot, definitely can't change the little numbers that are in the molecules. Okay, we can't just add a 3 or a 4. We can't change those little numbers there. They are locked in. That is what they are. They cannot be changed. That would change the structure or the identity of the molecule or the ionic compound, and we can't do that. So the only way that we can balance equations is by saying that we need more of a particular molecule. So we might need more waters. So we could put a 2 or a 3 in front. We'll see what happens in a second. But we need more than one water molecule. But we can't change the water molecule structure by saying I need 3 hydrogens to join onto the 1 oxygen. That changes it. It's no longer water anymore. It's something else. So we're going to balance the equation now doing that. So the way we're going to do that is we're going to take a bit of a stock take of all of the elements or the atoms that are currently on the left side and on the right side. We're going to do that by just writing each element that is present down so we can do a bit of a count. So I've got sodium written here. Now, how many sodiums do I have? Well, there's no number in front of the sodiums here, so we can assume it's a 1. So we have 1 sodium metal atom. Okay. How many hydrogens do we have? Well, we've got 2 hydrogens. We have 1 water molecule, which contains 2 hydrogen atoms. So we're going to put a 2 here. And how many oxygens do I have? Well, I have 1 oxygen currently. Okay, so that's what I have on the left side. What do I have on the right side? It's doing the same color. So we're going to keep track of the sodiums on this side. Okay, so how many sodiums do I have on this side? Well, I've only got the 1. So I've got 1 sodium. How many oxygens do I have? Well, there's only 1 oxygen here in the hydroxide ion, so there's 1. And how many hydrogens do I have on the product side? Well, I've got 1 here in the hydroxide ion, and I've actually got 2 here in the hydrogen gas molecule. So I've actually got 1, 2, 3. I've got 3 hydrogens on this side. All right, so that's what we start with. That's as we've written the equation, that's what we've got. Now, if this equation is written perfectly, how it occurs in the real world, each of these numbers on the left and the right side will match up. Now, they nearly do. So we have 1 sodium on both sides. We have 1 oxygen on both sides. The problem is the hydrogens. All right, so we've got 2 hydrogens on the left, and we've got 3 hydrogens on the right. That's the problem. At the moment, we've somehow magically made an extra hydrogen appear on the right side where it wasn't on the left. So we've got to account for that. We've got to fix that. So what we've got to do is this. We are going to have to look at where we can add some coefficients to increase the number of hydrogens on the left side. So at the moment we have 2, we need at least 3. The only place that hydrogens exist is in the water molecule. So we have to change the number in front of the water molecule. So I'm going to place a 2 there, if it will draw. There we go. That 2 tells me now that I have 2 water molecules on this side reacting. I'm going to draw the second one in so we can see it. It's a bit messy, but you get the picture. So that big 2 says we've now got 2 water molecules. All right, so we've times them together. There's 2 of them. What we now need to do is do a recount of the atoms that we have. So instead of, before we only had 2 hydrogens because we had 1 water, now we've got 1, 2, 3, 4 hydrogens. 2 times 2 is 4. So we've actually got 4 hydrogens now. And how many oxygens do we have? Well, before we only had 1, but now we've got 2 water molecules, so we've actually got 2 oxygens. So we're going to cross that off and put a 2. Now it looks like we've broken this thing a little bit more because now we've screwed up the oxygens, right? And the hydrogens still don't match. But balancing equations, there's a process, right? So we've started the process. So now we've got to look to the right side and go, okay, so how can we've got these numbers that don't quite match up. How can we maybe fix that? All right, so let's start with the hydrogens. Actually, no, let's start with the oxygens because the oxygens are only in one spot. Can you see how the oxygen's only in one molecule, whereas the hydrogen's in 2? So, little hint, always start with where there's only, an element is only in one molecule. Let's balance him first. So let's balance the oxygens. We had 2 on this side, we need 2 on the right side. So we're going to have to put a big 2 in front here so that we now have 2 sodium hydroxide units. So I'm going to put another one there. So the big 2 says we've now got 2 of these. That means we've got 2 oxygens, which is what we want. What else has it done? Well, it's made sure we've actually now got 2 times the sodiums as well. So we've added an extra sodium. We've also added another hydrogen. So we've got 2 hydrogens here, and we've got 2 hydrogens still over in this molecule. So that makes 4 altogether. Now let's have a look. That's actually helped us a lot. We've now balanced our hydrogens. Have a look. They're the same. We've also balanced our oxygens. They're the same. That's good. The only thing we've got left now is to fix is the sodiums. We've got 2 sodiums on this side. We've only got 1 on this side. So what have we got to do over here? Nice and easy. We put a big 2 in front. It means we need 2 sodium atoms. And now these guys are also the same. And we are balanced. We are happy. We have conserved mass. So if you really want to, you can put a 1 in front of that. So our balanced equation for sodium metal reacting with water is that, and this might help you understand, 2 sodium metal atoms react with 2 water molecules to make 1 hydrogen gas molecule and 2 sodium hydroxide crystals, right? Which are joined together. That's how we balance an equation and balance a reaction. I hope that was helpful. We have to do that because we have to conserve mass. We're not just magically putting numbers in front. We have to do that. It's part of the process. But remember, the key takeaways for balancing equations is this. Number 1, write each of the individual molecules or ionic compounds down first so that you lock in your little numbers. They cannot change. And then do a stock take on both sides of your elements. Okay, left and right, and then start changing the coefficients so that you can eventually balance the equations. The coefficients are the big numbers, and you may need to change them more than once. That helps you balance. Remember, a couple of quick hints. Leave oxygen and hydrogen till last. That would be a hint of mine, if possible, and balance the metals and the other non-metals first, so sodiums and that sort of stuff, if possible. The other thing is balance elements that are in one place on each side first before you start balancing elements that are in multiple molecules. So for example, we left hydrogen here till last because he was in multiple molecules. It means he can be fixed later on, whereas oxygen was only in 1. Anyway, look, I hope that was helpful. I'll do one more video where we do a heap of them. So if you need to, you can watch that one. Thanks, guys.